So with Amazon, their managed service, unlike Google calls it data product, they call it EMR. To get to it, you would just go to EMR here and kind of take a look at the way it works. And you can see here that I have some other clusters I'd set up earlier. So a couple things to be aware of is that probably the easiest way to get started on Amazon's EMR system is to use a notebook. And what I'm going to do is I'm going to click on notebook here, and I'm going to say create a notebook. Now, one of the things that comes up when you create a notebook is that it's going to ask you about cluster creation, and we'll get into that in a second. So I'm just going to say, hello UNCC, and that will be the name of this notebook, and we'll say this is a Spark Jupyter notebook. Now, what's kind of neat about this is that you could have an existing cluster that someone set up for you that's doing a bunch of stuff. Maybe every night it collects data or it runs a bunch of jobs for data scientists. And many companies I've worked with have had this, right? So there's a cluster and you need to talk to the existing cluster. In this particular case, though, what we're going to do is we're going to create a cluster because there's no clusters running. So if I click on create a cluster, it will bring up some options for me. What's nice about this interface is it streamlines things and it makes it a little bit more simple. Later, I'll show you a more advanced way to get things set up here, but you can see here that it will put Hadoop on there, it'll put Spark on there, and some other kind of Hadoop ecosystem applications. Next up here, I'll just leave everything default. And the only other thing that's really relevant is that you can refer to this S3 location, and that will be where your notebook is actually stored. So go ahead and create this notebook here. Go ahead and do that. And you can see here it's starting the notebook for cluster J2. Now, what's really useful about this particular setup is that it really streamlines how quick and easy it is to do data science, data engineering with EMR. And this is a relatively new feature. And I guess you could call it a little bit easier than the GCP cloud. And so I'm going to close some of these things I had up earlier here and just leave just the GCP stuff running. And I'm going to show you some other parts of GCP. So if we click on clusters here, you can see that there's nothing running, but this one is actually starting, right? So you can see that it's not yet provisioned. And this particular cluster is really more of like for prototyping. In the real world, you're not going to have, it really doesn't make a lot of sense to spin up Spark to run one machine. Like, why would you run Spark? Why not just run a machine that, runs scikit-learn somewhere, right? The whole point of a Spark system is that you have a bunch of different nodes. In particular, a few things to point out, and we'll do this in a second. In fact, we'll just do it at the same time so we can do it in parallel, is that you'll have a master which delegates the commands to some location. So this is really the control node. You'll have core nodes and you'll have task nodes. So the difference between a core and a task node is that the core nodes really manage the file system, this distributed file system. So they give you advanced disk I/O, really storage. So that's part of why you're building a MapReduce system or a big data system, is that you get access to the really a distributed file system, and this would be the Hadoop distributed file system. The task nodes will be where you do the work. Now, a core node, I believe, can do tasks and also manage the file system. So I think what people typically do is they have a master, maybe a couple cores, and then they'll have maybe like also some dedicated task nodes. And so the Spark will kind of do its best to distribute the load amongst both the core and the task. But the core itself its primary purpose is to manage the distributed file system. So to give you better disk I/O. And so I guess there could be some tweaking you could do where maybe you want like high performance disks, or maybe provision disk I/O, or there's all kinds of things you could do to tune it to make it more powerful. So while this is running, I'm going to create another cluster that shows you something kind of neat here, which is like a more large scale realistic. And look, you can see here it says save up to 90% when running spot instances. So that's exactly what we're going to do. Let's create another cluster, and we'll call this one UNCC spot cluster. And in order to do this, we need to go to the advanced options here. And so in terms of the software, now I'm gonna have to pick all the software and everything. And so one thing to be aware of is I'm gonna select Jupyter Hub, and I'm gonna select Spark so that I have access to those. And there's some other options. I'll just leave everything the same, and I'll go ahead and say next here. Now, this is where I could tune my configuration. And if I was an advanced Spark user, I would go through and change a bunch of stuff here. I'm just going to keep it simple, and you can see here that look, they kind of give you like a recommended setup like by default. So why don't I go through here and leave it so that there's one master, 2 cores. Again, remember this is the storage, and then I'm going to grab, let's say 5 spot instances. So I'm going to build a pretty big cluster here, but because they're spot, if I click on spot, I actually can get a much better savings because because I'm bidding on unused resources. Now, this is another thing that I'm going to select, which is that this allows me to pick not just a particular machine, but like any machine that's kind of close, so that I still lower the price. Because in a distributed system, you really don't care about a particular type of machine. Really just, I want to run a bunch of machines, and if they're close to each other, let's just pick those. And then I'm also going to select, in this case, a bunch of subnets here, so that there's some failover capabilities. All right, that looks good. Let's see. In this case, let's go to spot here. We'll pick that. We'll pick spot units. Let's add let's say 8, because I think it says each instance counts as 4 units. So I'll have two core nodes, and then for the task nodes, again, let's just put 20. So it would be 5 task nodes. And let's just spin this thing up, leave everything the same here. And for the cluster, we'll call this UNCC spot cluster, like that. And then we got a big data cluster running in theory here if this spins up. So this will take a bit, right? You can see I'm provisioning this. Now, one of the things you can do to see what it is you did, and this is one of the dangers about what I just did, is that you could get yourself in big financial trouble if you don't be very careful about this and clean up the resources when you're done. So I'm going to go to EC2, and you should see a ton of machines are about to get spun up. So if I click on running instance here, if I look for instance state, let's see, if I look for pending right here. So if you look here, you can see that it's actually trying to spin up a bunch of resources. So we see one is running, which is, I believe, probably the master node I set up before. But then as more of these instances are grabbed and provisioned, you should see more and more of these pendings which should start spinning up. So that's one way to kind of keep track of what's happening with EMR is to do that. So yes, sure. I think one of the ways that you would do something like that, it's a good question, would be that you would maybe do like an ephemeral job. I believe that's actually a slightly complex. So I guess the question here is like, how could you automatically scale EMR jobs based on load? And that's a little bit tricky. And that's actually one of the most tricky problems in distributed computing. And they have this problem in film as well, is how do you automatically pick the correct number of nodes? And I don't think there's a perfect answer for it. You can absolutely, when you submit a job, you could tell the main Spark cluster to provision additional EC2 instances and add them, and then run your jobs on those nodes. So that's one way to kind of automatically scale. A little bit trickier to have a job manager that would automatically decide how to scale it up and scale it down, that I'm aware of. There may be some very sophisticated solutions for it, but I think the easiest way to do that probably would be to, as you launch a new job, provision temporarily spot instances, run the job on the spot instances, and then auto terminate those spot instances. Sure. And if we go to this notebook here, you can see that this notebook is ready. And again, this is just one node. So for playing around with Spark, I think this is probably what you want to just maybe initially get used to. And if we click on this, we can open up Jupyter. And again, what's cool about this is that it's sure. Yeah, so when you launch a Spark cluster, and in this case, I provision a bunch of spot instances that they're running forever until I shut them down, right? And so you can see them running inside of the EC2 dashboard. And this is something that any user of AWS should always look at, is look inside of your EC2 dashboard. And most students should never see things running here unless you intentionally set things up. If they're running, you're going to get billed for it. Yeah, so I would probably kill that. This is definitely, if you have resources running and you're not, running production workloads, this is where you go through and you could go through here and you could actually say instance terminate. And in particular, though, we also can terminate it from spot requests as well. There's another way to terminate instances. If I went here and I went to actions, I could say cancel spot request. I won't do this because I'm in the middle of doing something, but it'll actually say terminate the instance and the spot request. So if you have a deep learning instance that's running via spot request, this may be the place to do it, is cancel the request and also cancel the deeper learning instance as well. But in general, there should never be anything here running unless you're doing something temporarily. And when you're done, you should terminate all the instances. So so you can see here what's neat about this particular. Yep. So what's neat about this particular notebook is that this notebook will be very similar to like a regular Python, right? That you can, it looks like what you're probably used to. And so what I'm going to do here, let me just find real quick. There's EMR Pi AWS sample that I was playing with earlier. I'm just going to throw it in there and tweak it a little bit. So what I'm going to do is just paste some code in here and just tweak it a little bit. So I'm going to just take this out here, just remove that. And then I'm going to just reformat this it's unfortunately, there might be, I think there is actually a way to do this in Jupyter where you can do auto, more like Vim kind of things where you can, change things around a little bit. Basically here, what I'm going to do is I'm going to say partitions is equal to 30 or something like that. And this will just run an operation on the cluster. So if I say, I'll copy this as well so I can use it again, and I'll just run this. Oh, we need to change this because it's Python 3. So I'll go here and like this. So I'll put this sample into a gist so you get access to it. So there we go. Okay, so it says no module named PySpark. So what I need to do, well, first of all, let me just make this a gist so you get access to it. And I'll put this into Slack. It's a gist here. And PySpark, like that. So you could run something similar. Here we go. So inside of this notebook, I need to go to kernel, and I need to pick PySpark, because PySpark is basically running Python code on top of Java. So we'll go through here, we'll run this, and I'll say shift return. And it's going to go ahead and launch a connection with Spark and then run this function. That's really what Spark does in this, is it just runs a function a bunch of times. And you can see here that this Spark context, this thing, it will run parallelize, and it will map this function a bunch of times to and run it on whatever resources are available. So let's wait for this a second. You can see that it's starting, and then this one says, I think I had a problem with this before. Let me see if I can find a gist. I think I had one before. Did I fix this? No. Spark context. I think I need to change the Spark context. And instead of this, I fixed this before. This is kind of an irritating bug, is that I have to change the Spark context here. I think this is the thing that helped me. Yeah, this. I just need to change it to this. Okay. So Stack Overflow is definitely helpful. If in the old days they didn't have this and it was much more challenging. And then I can change this. This is also, let me update that gist. This I believe should work. So I'm going to go to this gist here and fix it so that it's not a bad gist. There we go. That looks better. Okay. So next up here, you can see the Spark job is running. And this is really what's happening is that it was able to finish, and you can see that it took 12 seconds to run this. Now, this is kind of a hello world again, because there's only one node, right? So what does it really even tell us? Now, if I want to make it take longer, I could add a 0 to this and it will just run more of these. So let's see if that works. So I'm going to say kernel interrupts. This is one thing that's a little bit buggy about this, is you have to interrupt the kernel and then restart it again, I've noticed. And then I'll say restart and run all. And I believe this should work. And I'm just going to tell it to run the function even more times, basically. Okay, this one is cranking. This should, and once it provisions up again, we'll be able to watch it in action inside of here. So I think this workflow is not bad, like for doing things with, because many people are already familiar with Jupyter. And if I again go to the Spark job progress here, we can see, look, it's still running. It's going to take a little longer because look, it needs to do 300 operations. In this case, it's done 94 of 300. You can see how long the elapsed time is, right? So you can kind of watch it in action, while it's running. It shows you the elapsed time. So let's just, as an example here, we can see that this took 17 seconds. This exact code took 17 seconds. So can we do better? That's really a good question. So I think we can. What we're going to do is remember we created this cluster here, this UNCC spot cluster. If I click on it, look, I've got a lot of resources here, right? And if I go to EC2, there should be a bunch of them now. If I sort by running, look, we have a bunch of instances now running, right? A ton of these. So what I can do here, and I think this is ready to run, is I'm going to make a new notebook, and I'm going to tell the notebook to talk to an existing cluster. So let's do this, and we'll call this UNCC big. We'll call this big cluster. There we go. And then instead of create a cluster, I'm going to do a different option, which is choose an existing cluster. I'm going to go to this UNCC spot cluster. And then I leave everything default here and say create notebook. What's neat about this is that it's almost instantaneous. There's almost nothing to do. The cluster is the thing that takes a long time. This is in the background, kind of creating all this stuff, and it's almost instant. And so I believe it's pretty much ready to go. And it's a new notebook that AWS is running for you. I'm going to go here and I'm going to change the kernel to PySpark. And then I'm going to paste the code in here that I did before. But remember, I had 30, right? Because I want to do an apples to apples comparison. We know that this notebook with just one master node took 17 seconds. So this one has many more. It has, I think, 2 core nodes and also 5 task nodes. So it's got 7 nodes it can run this job on. So this should be much faster. Let's run it and let's see what happens. And we go through and we run this. So there's always a fixed cost overhead when you're doing a job, right? Like it's got to talk to the cluster, so you see the biggest benefit when you're running a giant job, like a terabyte job with all kinds of work or whatever. But this should be instructive in that it should be significantly faster because we have tons of tons of nodes that we're running this on. And in fact, it was right. So you can see that before it was 17 seconds, right? And then in this case, this was 6 seconds. So I guess we could do one final test here, which is let's make it even busier. Let's make this one, let's add another 0 to it, make it 3000. And I will interrupt the kernel here, and then say restart and run all. I don't know why I've had to do that, but that workflow seems to be the best. So this should take a while. And then I'm also going to do the same thing here. I'm going to interrupt, and then I'm going to paste in this new code here, which just adds another 0. I'm going to restart and run all, and then we'll just have a race, right? We have basically like a Ford Pinto, and then we have like a Maserati, and they're racing. We're going to see who finishes the lap on the track faster. And so this one's starting up. Again, this just has one node here. Let's see what it's doing. You can see it's got to do 3,000 operations, and I guess you could kind of ballpark it. It's like 7 seconds for every 30 or something. So you could say 7. I don't know, by let's say 1,000. 7,000, would it be 7,000 seconds? Maybe my math is wrong. Maybe it's 700 seconds, but it's going to take a bit of time. So it's still crunching. I guess an easier way would be times this by 10, so it'll be 280 seconds. So I was off by quite a bit. So we'll say it'll take probably 280 seconds. Now let's go back to our big cluster here, and let's look at this. Look, already done, right? So you really start to see the big cluster, why it's useful when you get into a bigger job. So this one only took 20 seconds. This one is just still struggling, right? Like we're not even a third of the way done. And this one finished a long time ago. Took 20 seconds, right? Makes sense? So what's the last thing we should do here? Sure. Let's see here. The partitions. Where do you see partitions? Yeah. So the idea here is that this is the parallel code, and this Spark context itself is what allows you to map a function inside of the distributed cluster. And when we say SC parallelize here, really all this is doing is that it's saying take this function and run it this many times, basically. So basically the larger this n number is, you can see that the partitions basically just makes the number bigger. So basically, how many times you want this function to run, it would be a little different in a more realistic scenario where you split things up again. But the high level is that it just tells it how many times, the larger the n is, the more times this function will be run. Exactly. So that's exactly right. So what would happen is that in a more realistic example is that you have a embarrassingly parallel problem, and like training a machine learning model, for example, like Spark has something called Spark MLlib, and you can train a model. We know that GPUs are very fast, and you could have Spark attached to a bunch of GPUs, and you could train a big distributed model. And that's behind the scenes. That's what it would be doing. It would be taking something and putting a little piece on each one of the nodes so that it runs in parallel. And that's really the use case for something like Spark, is like, do you have something that can be run in parallel where you're bottlenecked on CPU, disk IO, memory, and you're able to basically run that and distribute it around. So I guess another good one would be, and I put this, I believe, earlier as an example in the project. And if let me just show this real quick, is if I go here, I think I updated the projects here to just show a couple other things. Projects in the course that in particular, let's see here. We got this. Let me show you. So I did update. There's some other things here, but the main thing I wanted to show you was Gutenberg free text, free books, or something like that. There's a source where you can, I think it's this Gutenberg. And if I went to, like, I don't know, Romeo and Juliet, let's say that you wanted to download this, and I'll throw this into like a Slack channel. Let's say you wanted to download this, and you want to count how many occurrences of every word that appears in Romeo and Juliet. That would be a classic example of like how you could figure something like that out into a MapReduce. And if we look at this link here, I believe this example, you could see how how you would do something like that. Here's our input, which would be, let's say again, the Romeo and Juliet file. First, you split the data up so that you have a bunch of different pieces of the file essentially, and then the map part would be the part would be the function that we wrote, right? You could just say, okay, the word, here we go. I found this word, and this word is like Romeo, right? And I put 1 to it, and so you're basically you're appending this number to every single word. Then you shuffle the data so that all the words appear together, and then the reduce would go through, and you would basically find you would essentially sum together all the occurrences of that word, and then your final result would be that. So that would be, if that was something you wanted to do, to basically count all occurrences of a word. And again, you could, if you wanted this to be your example of your project, like this could be an interesting one, or some other piece of free text. I think that would be a good fit to play around with this, to test your understanding of this. And so why does someone do this? Like, what's the point of like running? The big issue here is that it's a little bit subtle, but when you're doing an operation on this, especially in the real world, you're going to be bound not just by the CPU, you're also bound by the disk, and the disk IO in particular. So every time you go and you talk to the disk, you're making it slower. And when you run a distributed job, like film companies, this is a big deal. Like, I spent a lot of my time working in life in film, and the file server would get slow because it has a fixed amount. And so that's why they typically will split up a job with many different file servers. And that's really what the Hadoop file system is. It's just a bunch of different machines. Each one of them has a capacity for how fast the disk runs, and you're using each one of the disk's capacity to parallelize the job, in addition to the memory, in addition to the CPU. Great. So I will just stop this.